Welcome back, everyone. We are talking about metrics at the moment. And for the rest of the term, actually, we will be talking about pseudo-Riemannian metrics. So just to recall the basic things. So a pseudo-Riemannian metric is something of this sort. That component G mu nu, which in general, of course, depends on x. Dx mu, dx nu. So that's a tensor field of second rank covariant. And it was supposed to have two properties. It should be symmetric and it should be non-degenerate. This allows to invert the metric, so we can then introduce something which I occasionally will denote by g to the minus 1. This is g mu nu, which of course also depends on x, d mu partial d nu. So this has now both indices, in the upper position, so it's a contravariant tensor field, okay? And this is defined by, if I know this thing, then I can construct the inverse metric just by inverting the coordinate matrix. So G mu nu, G nu sigma should be Kronecker mu sigma. And the same, of course, if I do it the other way around. G sigma tau, G tau mu. Okay, and with the help of these two things, we can raise and lower indices. I think this was the last thing I discussed last week. And we are just in the process of listing a couple of properties. And the next properties I want to discuss is that with the help of such a thing, we can introduce something which we will call the autocomplement of a vector. Namely, for any vector xp in the tangent space at a point M, we define the autocomplement that's with an E, I think. Complement, of course, this refers to the metric. So just to make sure this fact, let me write with respect to G. And the autocomplement, so you could denote this in this way. It's a set. It's not a vector, it's a set. It's a set of all vectors which are perpendicular to xp. So sometimes they are noted by xp perp. And they are defined as the vectors, as a set of all vectors in TPM, which are perpendicular with respect to this matrix. This means if I feed my given xp in one slot and yp in the other slot, then I get 0. So this is read by saying that the vector yp is perpendicular to the vector xp with respect to this metric. And what this geometrically means, this depends quite strongly on the character of the pseudo-Riemannian metric. There are pseudo-Riemannian metrics of different type, and we will make this distinction in a minute. But there's one fact which is universal, one property of the autocomplement which is universal for any pseudo-Riemannian metric. That's the fact that it always has a codimension of the one-dimensional space spanned by xp, and that's because of the non-degeneracy. Because of the non-degeneracy, that's this property here. That's what we call non-degeneracy. Because of non-degeneracy, this space xp, this set, it's a vector space, obviously. If I have two vectors, yp1 and yp2, which satisfy this property, then the linear combination also satisfies this property. So this is a vector space. And the question is, what's the dimension of this vector space? And this follows from the non-degeneracy. This means that we can invert this equation in a sense. And so this must have the codimension, has dimension n minus 1. Where n is the dimension of the manifold, where TPM is n-dimensional. So that's universal. But what is not universal is whether this space, together with the vector xp, spans the whole space. Or if maybe it is possible that the vector xp is contained in this order complement. That's actually possible. This depends on the type of the metric. So what do I mean by type? Well, we can classify these pseudo-Riemannian metrics according to what is called the signature. So what is this? Well, we observe that this is symmetric. And now I hope you remember from elementary linear algebra that a symmetric matrix can always be diagonalized. So, well, to put this more precisely, if I have a bilinear form on a vector space, which is symmetric, then I can always find a basis such that it is diagonal. So I can always find a basis such that the basis vectors are perpendicular in this sense to each other. So this means I can always diagonalize this matrix G mu nu. Let me write this down first. So because of symmetry, and by symmetry I mean this here, G mu nu is the same as G mu mu. The matrix G mu nu, which depends on x, this can be diagonalized. Diagonalized at any point x. Of course, I have to do this independent of the point. The question if we can diagonalize this matrix on a whole neighborhood, so for all x in a neighborhood simultaneously, that's a different question. And actually to this question the answer will be no. But if I pick one point, I go to one point, then I get this symmetric matrix, G mu nu, at this point, and this can be diagonalized. I can always arrange my coordinates in such a way that this matrix here becomes diagonal. And because of the non-degeneracy, the diagonal elements are all non-zero. Yeah? If one of the diagonal elements would be 0, then the matrix would have a kernel, so it would not be degenerate. So because of non-degeneracy, the diagonal elements are non-zero. This means there are a number of positive elements and a number of negative elements in the diagonal, but not a 0. But, well, I can make the positive elements equal to +1 and the negative elements equal to -1 just by stretching the axis. Yeah, if I make the axis shorter or longer, then I can give any non-zero value to these diagonal elements I like. So let me write by stretching the axis. Yeah, I hope you understand what I mean. So that's not very precise mathematical language. By stretching the axis, the diagonal elements can be made to a sequence of a certain number of -1s and then a sequence of a certain number of +1s. And this sequence is what we call the signature of the pseudo-Riemannian metric. The sequence is called the signature of G. So when I said there are pseudo-Riemannian metrics of different type, I meant there are pseudo-Riemannian metrics of different signature. And actually the geometric properties of the pseudo-Riemannian metric depends very strongly on the signature. So I should also mention that some people use the word signature in a different way. So I really mean the sequence. So I give a certain number of minus signs and then a certain number of plus signs. Some people mean the number of, number of plus signs minus the number of minus signs. That's what they call the signature, which contains essentially the same information, right? Okay, this was at one point. So I go to one point, I diagonalize my matrix, then I stretch the axis, and then I get the sequence. Yeah, I get a diagonal matrix with this sequence. And of course, I can do this at any point. And the question is, can the sequence depend on the point? So is it possible that at one point I get 5 minus signs and 3 plus signs, and at the other point I get 6 minus signs and 2 plus signs? Is this possible? What do you think? Any suggestion? So the question is, can the signature depend on the point according to how we introduce pseudo-Riemannian metrics? Some of you are shaking the head. In fact, it cannot depend on the point. Why not? Which property of G assures that it cannot, well, properties, I should say. Which two properties assure that this cannot be the case? Well, with this sign, you remember what we meant by this sign? We meant these are tensor fields which are C infinity tensor fields. So they depend in particular continuously on the foot point. And if we would have a change of signature, this would mean that the properties of the matrix G mu nu would change discontinuously. Yeah? If I had, well, this is necessary because of the second property, which is the non-degeneracy. The non-degeneracy assures that the diagonal elements can never go through zero. But how should they jump from a positive to a negative value in a continuous manner without going through zero, right? So the two properties, continuity and non-degeneracy, they guarantee that the signature cannot depend on the point. So it characterizes the metric as a whole. So every metric has a fixed signature. So the signature, because of continuity and non-degeneracy, the signature is independent of x. I cannot squeeze it here. Is independent of x. Yeah, of the point. So it characterizes the metric uniquely. Well, now we can discuss different types of signature, depending on how many minus signs we have in this sequence. And there are two types which are particularly interesting. The first type is the one where we have no minus signs at all, where we have only plus signs. That's what we call a Riemannian metric, without pseudo, because that's the thing which Bernhard Riemann actually discussed in the 19th century. He didn't have minus signs here. So minus signs were introduced later. And for this later structure, then people used the new words. They needed the new words. They called it pseudo-Riemannian, or sometimes semi-Riemannian. So the ordinary Riemannian signature is the one without minus signs. So that's the first type which is of interest. And the type which is of interest for us is, of course, the one with just one minus sign. That's what we need for our space-time geometry. One minus sign and 3 plus signs. That's the structure we know from special relativity, right? And the idea of this whole approach using the equivalence principle was to mimic the structure of special relativity in infinitesimally small regions on the tangent space. It means at one point we want to have such a structure. So let me write, there are two types of signature. Are especially important. So the first is the one without minus signs. I have only plus signs. That's what we call Riemannian metrics. This means that this expression, no, not with different entries. So then I have GP, XP, XP bigger than 0 for all XP which are not the 0 vector. For the 0 vector, of course, I get 0, right? But for any other one, I get something which is bigger. And then I can interpret this as a square of a length. If it's positive, I can take the square root. And that's what we call the length of the vector, as it is defined by this Riemannian metric. Can be interpreted as length. So that's, of course, where the word metric comes from, right? Because it allows you to measure the length of a vector. It gives a definite value to the length of a vector. And this whole theory, as I said already, was originally made for this positive definite case where this is really positive, so we can interpret it as a length for any vector xp. And another important thing is that in this case, the autocomplement is linearly independent of the metric. So because this is non-zero, yeah, unless xp is a zero vector. So whenever I have a xp different from 0, this is not 0. This means the vector xp is not orthogonal to itself. So it's not contained in its own autocomplement. Yeah, it's linearly independent of its autocomplement. So the vector itself and its autocomplement span the whole space. That's an important property in this for this signature, not for arbitrary signature. Then xp perp and xp span all of TPM. So the geometric picture is really, as you would imagine, if you speak of an autocomplement, if this is xp perp, then you would really have the vector always as linearly independent. So the two things together span everything. So every vector can be written as a linear combination of a multiple of xp and a vector which is perpendicular to xp. This holds for this signature. Okay, that's a standard case of a Riemannian manifold. Yeah, a manifold with a Riemannian metric is also called a Riemannian manifold. And that's what Riemann developed and was then what was then further developed in many, many textbooks. So if you go to the library and look at Riemannian manifolds or Riemannian geometry, then you find many, many books which deal with precisely this thing. But that's not what we are interested in if we want to do general relativity. We need a different signature. We want to mimic the structure which was present in special relativity, and there we had one minus sign. So we are interested in the signature where we have one minus sign and then a number of plus signs. Actually, we have four-dimensional manifolds, so we have 3 plus signs. But at the moment, let's consider arbitrary dimension. And that's what is called a Lorentzian metric. So that's a term which has become common over the last 20 or 30 years. So one would also say it's a pseudo-Riemannian metric with Lorentzian signature. That's the same thing. And now there's because people had studied Riemannian metrics for many, many years, and they were used to calling this the square of the length. It is very common also in this case to call this the square of the length, which of course is actually nonsense because it can be negative, right? It cannot be the square of something real, but it's a common terminology. So then GP, XP, XP is not in general. Is not in general the square of a length. But nonetheless, it is often called the length squared. Some people say pseudo-length. So we can distinguish now 3 types of vectors, and that's what we know already from special relativity, namely the ones for which this is positive, for which this is negative, and for which this is 0. So this distinguishes the space-like, the light-like, and the time-like vectors. So we say the vector xp is time-like. I should say let's exclude the 0 vector because there's some controversy. What about the 0 vector? What's the causal character of the 0 vector? Let's exclude this. So we say it's time-like if this is negative. We say xp is light-like if this here is 0. Which of course is impossible in the Riemannian case, right? So it's a new feature that we can have vectors which are in their own autocomplement, which are perpendicular to themselves. And we say that xp is space-like if gp, xp, xp is bigger than 0. And for a light-like vector, we have for xp light-like, we have the intriguing property that xp is contained in its own autocomplement. Yeah? It's perpendicular to itself. So in this case, the picture looks not like that. So that's what we usually mean with autocomplement, yeah? That it's perpendicular in a geometrically intuitive way. But here we have the case that if this is xp perp, that the vector xp is in this space. Yeah? So the vector is perpendicular to itself. So if I have an arbitrary vector, I cannot write it as a linear combination of xp and a vector which is perpendicular to xp. Yeah? So this notion of an orthogonal decomposition doesn't work for light-like vectors. Okay, so these are the cases. And yeah, that's of course a case we are interested in for applications in physics, because then, well, this is what we have discussed here. This means that at any one point, now we can the matrix G mu nu to this form. That's what we called eta mu nu when we did special relativity, right? So we can, at any one point, we can make the G mu nu equal to the eta mu nu from special relativity. So each tangent space, which is attached to a particular point, carries the structure of the space-time of special relativity. It does not work in a whole neighborhood. Yeah? We haven't discussed this question until now. We will come to it in a minute. Namely to the question if we can do this on a whole neighborhood, not just at one point. And we will see immediately that in general it is not be possible. So let me write this remark here. For n equal 4, TPM has then the structure of the space-time of special relativity. Oops. And this was our program, to find a mathematical structure, yeah, a mathematical language in order to describe objects, spacetimes, where the structure in infinitesimally small regions is the same as in special relativity. This was a program motivated by the equivalence principle. And now we have succeeded in doing this. So if this is our M, then we have at each point, we have a tangent space, oops, TPM. And this tangent space looks like the space-time in special relativity. So in particular, we have this light cone, the set of all vectors which are light-like. And yeah, but this is given only on the tangent space. So here we can make the metric equal to eta mu nu. We can do this at any point, but not simultaneously. Yeah? We have to choose one point, and we can make at this point the metric equal to eta mu nu. But if somebody else wants to do it at another point, and maybe even in a whole neighborhood of one point, then in general it won't work. So if I have here the point P, that's TPM at this point, and at another point, let's say that's TQM. So here's a point Q. You would have this cone, but the cones do not fit together. So there's no notion which allows us to identify these tangent spaces. So as it is in special relativity, where I have just one vector space with this metric. Here, the whole thing really depends on the point where I am. So it's a translation of our physical idea that the equivalence principle should hold into mathematical language. That we have to consider a pseudo-Riemannian manifold of Lorentzian signature. And that's what we will do in the rest of the term. But let me list a few more properties of pseudo-Riemannian metrics. I will not specify to the Lorentzian case, so I will list a number of properties which are actually independent of the signature, which hold for any sort of signature. So the first thing I want to discuss is the notion of covariant derivatives on a manifold. Remember, we need an extra structure if we want to covariantly differentiate. this was a covariant derivative, what we denote by this nabla. So you might think if you have a pseudo-Riemannian manifold, and if you want to differentiate covariantly, you would have to introduce, in addition, a covariant derivative. But the situation is more convenient because every pseudo-Riemannian manifold comes automatically with a distinguished covariant derivative, which is called the Levi-Civita derivative. And that's what I want to formulate now. So I write this as a theorem. So the theorem says that when I have a pseudo-Riemannian manifold of any signature, this has nothing to do with the signature, then it comes automatically with a distinguished covariant derivative. So that's a theorem. So that's the way in which we write this, right? The manifold M together with a pseudo-Riemannian metric. So we write this as a pair. So let this be a manifold with a pseudo-Riemannian metric, and Riemannian metric. And the signature plays no role, so let me write of arbitrary signature. And now my claim is, then there is a unique covariant derivative del and this is called the Levi-Civita derivative or Levi-Civita connection. Remember, covariant derivative is the same as linear connection. Yeah, the two words are used interchangeably, called the Levi-Civita derivative, such that, so there are two properties which define the Levi-Civita connection or Levi-Civita derivative. The first is that it is torsion-free. Yeah, the torsion of del vanishes. And the second property is, so I could write this here in formula as this. As a t, we use the t for the torsion tensor of del. So this is supposed to be 0. And the second property is what is called metric. This means the following. This is a tensor field, so I can calculate covariant derivatives of this in the direction of any vector field z. This gives me again a tensor field of the same rank as G, and the claim is that this is 0 for all vector fields z. So then we say the connection is metric. We have talked already about the geometric meaning of this condition. This was a kind of closure condition when we parallel transported vectors along a mesh of curves. The geometric meaning of this here? Well, if we remember that we use a G in order to define this quantity, which is called the length, or the pseudo-length, if we have a non-positive matrix, then you see that this condition means that this property is not changed along a curve by parallel transport. So if I parallel transport a vector with the help of this connection along a curve, then its length or pseudo-length doesn't change if this condition holds. That's the geometric meaning of this here. And the claim is that these two properties are satisfied by precisely one connection. And that's called the Levi-Civita connection. Levi-Civita, by the way, was an Italian mathematician, highly esteemed by Albert Einstein. Einstein was once asked what was his favorite country, and he said Italy. And when people asked him why, he said because of spaghetti and Levi-Civita. So he liked him very much. He was also Jewish. And in contrast to Einstein, he did not emigrate when the fascists took over in Italy as well as in Germany. And in his last years, he was completely isolated. So he was in his home in Rome, and he was expelled from the university, of course. And he was completely isolated from all contacts. I think he died around 1940. He was a few years older than Einstein. So he was a very important person in the establishment of tensor calculus. Actually, one could say he was one of the two fathers of tensor calculus. The other one was his teacher, Ricci. Gregorio Ricci-Cubastro. Okay, so that's the statement, and well, the statement is so important that I want to prove it. And well, the first reason why I want to prove it is that the statement is important. The second reason is that the proof is constructive. It really tells us by which equation this del is characterized, and that's something we want to use in the following. The proof is fairly simple if you know how to do it. If you do not know how to do it, it's rather intriguing. So if you just start thinking about how to prove this, I doubt whether you would find how to do it. But if you have seen it once in a book how it works, then it's very easy to do it again. So let me show this. So I begin with uniqueness. So I want to show that if a connection has these properties, that then it is unique. And I do this in the following way. I assume that del satisfies these two properties, satisfies A and B. And my goal is to derive an equation which characterizes this del then uniquely. Yeah, that's my goal. And how do you do this? Well, you begin by writing, oh, I think I need more space for this. I should do this on the other board, because I need a couple of equations, one underneath the other. Which equation I begin? X, Y, Z, yes. So then, so I can do the following. I can apply a derivative x. Yeah, that's a vector field. So it means it's something which operates on functions as a derivative operator. I can apply this to this function. Yeah? It's a scalar valued function, a tensor field of type OO, if you like to call it this way, and I apply this derivative. And now I use the product rule. So this is, if I write it out, del xg of yz plus g del xyz plus gy del xz. Okay? And now this is 0 by assumption. We assume that our connection is 0. So we get x gy z is this here. And here I can turn around the order by using the fact that the torsion vanishes. For which term I do this? Let me check this. And I have the same letters as I have in my notes. X, I do it with the second one. So I keep the first as it was, g del xyz. And here I want to write gy del zx, the other way around. So I can do this if I remember the definition of the torsion. The definition of the torsion was that the torsion of x comma z is this minus that minus this minus a Lie bracket. So if I put the Lie bracket here, x of z, then I have equality. So this is, in general, no, only this expression here. This is del zx plus xz plus torsion xz. Yeah? If you remember the definition of the torsion. Definition of the torsion was that this minus this minus this. If I take these two to the other side, then I get this is a torsion, and the torsion is 0 by assumption. So this here is 0, and then I get this here. So I get, in the end, this expression here. And now I write the same equation 2 times more with the vectors interchanged, the vector fields interchanged. This holds for all vector fields x, y, z, right? So it also holds if I interchange them, and I do this cyclically. So I get this here, del yzx plus g z del xy plus yx. Okay? It is the same equation, just I make the x into y, the y into z, and the z into x. And I do this another time. I again interchange cyclically, and I get this here. Del zx y plus z g of x del yz plus z y. Now I have three equations, and I subtract the last one from the first two. So I put a minus here, and a minus here. And I add these three things together. What do I get then? And I get x gyz plus y gzx minus z gxy. And I get these three terms here on the other side. So I have g x y z plus z yzx minus z y. And then I get these three terms. So I get plus y del zx. I take this one next, g z del xy, and this one here, minus gx del yz. And now the three terms with the Lie bracket, plus g y xz plus gz yx minus gx y. And now comes the intriguing moment where I check if four terms cancel. Let me see if I got all the signs right. So yes, this, oh no, I did not get all signs right. Let me see. Where do I have a y in one slot, an isolated y in one slot? In these two terms, del zx, that's the same. G is symmetric. Yeah? It doesn't matter if I interchange the two slots. Yeah? G is symmetric. So these two terms cancel, and hopefully this also cancels again. Yes, against this here. So these also cancel. And now I can solve, and this is two times the same, right? I can solve for this expression. So, oh, let me continue here. So I get 2 times g del xyz, and then only the Lie bracket terms, plus gy xz plus gz yx minus gs zx. So you might say, what's the purpose of all this? Just calculating around with these expressions. Well, now we have achieved the following goal. There's only one term which involves a covariant derivative. This is this term here. All the other ones do not involve covariant derivatives. So if we solve for this expression, we know what the covariant derivative does with any vector field. Because of the non-degeneracy, if I know what the scalar product with any z is, I know this expression. Yeah? So if I solve for this expression, I get an expression which determines the covariant derivative uniquely. And that was the goal of the whole thing. We wanted to prove that these two properties A and B, which we have used in the calculation, determine the covariant derivative uniquely. So I solve for this expression, and then I get what? Del x y, that is 1/2 times something. Yeah, it's this 2. I take this 2 to the other side, and then I get a couple of terms. I get x gyz plus y gxz minus z gxy, and then the Lie bracket terms, plus g, no, minus, this comes to the other side, minus gy xz minus gz yx minus gx zx. So if I want to know what is this, then this equation tells me what this is for any pair of vector fields x and y. Yeah? Because if I know what the scalar product with z is, I know this expression because of the non-degeneracy. And what the scalar product with z is tells me this equation. If you give me the 3 vector fields, I can calculate each of these terms. So it gives me this here. So I know what the covariant derivative does. So this this proves uniqueness. So if a covariant derivative with these two properties A and B exists, then it must be determined by this equation. The question is, does this equation indeed determine a covariant derivative? That's the question about existence. Well, I don't demonstrate this in detail. What you have to check is clear, right? You have to check if this expression is linear in this slot and derivative has a derivative property in this slot. So if you write here a linear combination, then it must be possible to use the distributive law. And if you write a linear combination here, it must be possible to evaluate this with the product rule. Yeah? So this has to be worked out for these 6 terms on the right-hand side. There's a bracket missing, I just see. So so I just write it as straightforward. To prove that this equation here, let's call this star, that star has all properties of a covariant derivative. Yeah, remember how we define covariant derivatives. This operator was supposed to have a number of properties, exactly 2 properties, linearity in this slot and the derivative property in the other slot. And well, this is just by writing this out. It's a boring task. I don't want to do this here on the board. Has all properties of a covariant derivative, and this proves existence. So this is a proof that the Levi-Civita connection exists and that it is unique. And the proof is constructive in the sense that it really gives us an equation the covariant derivative has to satisfy. So this completes the proof. And from this proof, we get immediately an expression for the Levi-Civita connection. In particular, we get an expression for the Christoffel symbols of the Levi-Civita connection. Because if we insert basis vector fields here, then this is just the expressible in terms of the Christoffel symbols. So this equation star determines the Christoffel symbols of the Levi-Civita connection. And we will derive this equation because it's actually a very important equation. When you calculate the Christoffel symbols of the Levi-Civita connection, you will always use this equation and not some other property of connection coefficients of Christoffel symbols in the following way. So all I have to do is I have to choose for x, y, z basis vectors in a coordinate basis. So I have to calculate what is this here. If I introduce here d mu, d nu, d sigma, say. What do I get on the right-hand side? I get 1/2 times what? So the x is now d mu, right? And this acts on G where I fill the d nu in the first slot and d sigma in the second slot. That's just my coefficient G mu sigma. Yeah? For the second term, I have the d nu, and this is applied to G mu sigma. And here I have the d sigma. This comes with a minus. So I have 3 terms. The first 2 come with a plus. The second comes with a minus. The third comes with a minus. G mu nu, right? So what are the remaining terms? Question to the audience. If I feed basis vector fields, d mu, d nu, d sigma into a Lie bracket, what do I get? The Lie bracket is a commutator, remember. Yeah? What's a commutator of partial derivatives? 0. Yeah? So that's it. That's it. Oh, let me write plus 0. Plus 0, minus 0. Yeah, if you like, or the other way. Okay. Did I make a sign mistake here? I think also one term should have a different sign than the other. So I brought this gets a minus, this gets a minus, the last one should get a plus, right? So I should have a plus here. So here it is this. For this calculation it's irrelevant because they are 0 anyway. Yeah, but in general it is important to have the right sign. So and what we get here, this can be expressed in terms of the Christoffel symbols, right? Remember, that's how we introduce the Christoffel symbols. So we get now g tau mu nu, and then the tau in the first slot of g, the sigma in the second slot. So this is just g tau sigma. And here I have again this expression. Plus d nu, g mu sigma, d sigma, g mu nu. And this can be solved for the Christoffel symbols if I use the inverse of this here. So I need the inverse with an upper index sigma, right? And let's say lambda. Then I get a Kronecker here. So I get gamma tau mu nu. I get a Kronecker lambda tau. Yeah, okay, let me write it in 2 steps. So I get this here. This is this here. 1/2 d mu minus d sigma g mu nu. And this is a Kronecker delta lambda tau. So this replaces the tau by a lambda. So what we have on the left-hand side is just gamma lambda mu nu. So this expression gives me the gammas. So that's the same statement which we have observed already here, namely that this equation determines the connection uniquely. This can also read from this equation. Yeah, it tells us what the gammas are. And if I know the gammas, then I know the connection. Yeah, the gammas contain the same information as a connection. So they are calculated in this way. So if you give me the metric, then I can calculate the Christoffel symbols of the Levi-Civita connection just by calculating derivatives. Well, what did I do? I forgot this here. That's quite important. G sigma lambda. Yeah, I need the inverse matrix on the right-hand side, of course. So this comes here. Are the indices correct? Let me check. Sigma lambda, sigma. Yes, it looks good. Mm-hmm. Okay. So one can check that also from this coordinate expression you can check that the Levi-Civita connection has the 2 properties by which it was defined. It was defined by 2 properties, vanishing torsion and metricity. And of course this must be reflected also in this coordinate expression. So vanishing torsion. What does this mean? You remember what has a torsion to do with the gammas? So if I want to check with this coordinate expression for the gammas of if the connection is torsion free, what do I have to do? Remember? What was a torsion in coordinates? How was it related to the gammas? Don't remember? Or just the anti-symmetrization with respect to the 2 lower indices. Yeah? So the T, what are the indices? Lambda mu nu was defined. Oh no, it was not defined, sorry. It could be expressed in terms of the Christoffel symbol by this expression. And if we have vanishing torsion, and this must of course be 0. Well, I think you can do this without writing anything down, just by looking at the expression. If I interchange mu and nu, these 2 terms swap places, right? But as a sum, they remain the same. And this term is symmetric. Yeah? So the whole thing is symmetric. So that's obvious. And the other property is the metricity. Well, that's a little bit, there you have to calculate a little bit. I think you don't see it just by looking at the expression. What we have to show is that the covariant derivative of the metric is 0. And how would you calculate this? Well, you would express a covariant derivative by partial derivatives. We have learned how to do this. So this would be the partial derivatives, and then for each index, there comes a correction term, which involves the gammas. So the first, and it comes with a minus sign for covariant indices, for downstairs indices. So I have here gamma, what is this? If I replace the sigma, I have a mu tau and a new index lambda, g, no, wait a minute, what am I doing? Mu tau. Then the sigma is left, and I replace the tau. That's the correct thing. Minus gamma lambda, and I now do it for the other index, for the sigma. So I get the sigma here on the gamma. Sigma tau g. The sigma becomes a lambda, and the summation and the other index is the tau, right? So that's it. And this is also supposed to be 0. So if you insert the gammas from this expression and rearrange the terms a little bit, you will find that this is 0. Yeah, this is. I think you cannot see this just by looking at the expression, but if you don't believe it, it should not be too difficult to verify. I have 2 taus here. What have I done? I always make mistakes with the indices. So let me see. The mu, the first index is always a mu. The derivative is with respect to mu. And then I replace lambda, I replace the sigma, so I would have the sigma here, right? So the first index on the gamma is always the index with respect to which the derivative is done, so that's always a mu. And in these terms, the index which comes in the second place of the gamma is the index I replace here. So here I replace tau by lambda, and here I replace sigma by lambda. Yes, now it's correct. Okay. So that's the general formula how a covariant derivative can be expressed in terms of partial derivatives. So that's a Levi-Civita connection. So we don't have to introduce a covariant derivative separately, right? Any pseudo-Riemannian metric comes with a covariant derivative automatically. Well, the fact that the covariant derivative is metric, this property that this is 0, this has an important consequence in view of our rule of shifting indices. If this would not hold, then we would have to be very careful with shifting indices under a derivative, under a covariant derivative, because this would require to pull the g under the derivative. And if this would not be covariantly constant, then it would be given an additional term, right? But this rule allows us to lower and raise indices independently of whether they are under a derivative. Let me write this down. So I have some space here. Oops. So because of this rule, indices can be raised or lowered under a covariant derivative. So let's do a little example. So if I have an equation of this sort, let's say I have a derivative of a what example do I do? I think I should do the same example which I have here in the notes. I do it just for a covector field. So I start with a vector field. So I have an x with an upper index. So this would be something of this type, right? A tensor of rank 1, 1. And I want to lower the index. I want to lower this index sigma. So from this, of course, I get that I can multiply this with g sigma nu. Then I would have here this here. Yeah. So on the right-hand side, I just get the expression with a lowered index. But here I have to be a little bit careful, because if I want to lower this index, this requires to pull the g under the derivative, right? So let me do it in full detail. So what I have to do is I would use this product rule. So I would write this in this way. Minus x sigma del mu g sigma nu. And on the right-hand side, I have just S mu nu. And now you see, fortunately, this here is 0. So one equation follows from the preceding one, yeah? And from this here now we get, now we have the x with a lowered index. So this is now x, x nu is s mu nu, yeah? So if you have done this once in your life, then you just remember as a rule, I can raise or lower indices under the covariant derivative. I don't have to be careful about this. But you do have to be careful if this is a partial derivative. Yeah? Because for partial derivatives, this does not hold. The partial derivative here, of course, would not be 0. So this rule does not hold for partial derivatives. Yeah, obviously. Because if I replace a covariant derivative by a partial derivative here, then this would not be 0. And you would get this second term on the left-hand side. Okay. Now, oh my goodness. Yeah. Next thing I want to talk about is the geodesic equation. We have talked about geodesics of arbitrary connections, and now we can talk about the geodesics of the Levi-Civita connection, which actually has very special properties, very nice properties in comparison to an arbitrary connection. In particular, it can be derived from a variational principle, and that's what I want to demonstrate now. That's not true for an arbitrary, for the geodesics of an arbitrary connection. So remember how geodesics were introduced? We introduced them as, in quotation marks, straightest lines with respect to a connection. So a curve was called a geodesic if its tangent field is parallel transported along the curve. So the tangent field is parallel along the curve, then we call it a geodesic. Some people call it an autoparallel, that's the same. And we want now to do this for the geodesics of the Levi-Civita connection. So we want to express these geodesics with the help of the metric from which the Levi-Civita connection was derived. And what we want to demonstrate is that actually the geodesics are the solutions of a variational principle. Now I strongly hope that you remember from classical mechanics that there's a thing which is called the Lagrange formalism. I hope everybody has encountered this and remembers that there's a certain variational principle called Hamilton's principle, which allows to write certain types of ordinary differential equations as the solutions of a variational principle. That's what I want to use now. So I will write down a Lagrangian, and I will then demonstrate that the solution curves which derive from this Lagrangian are indeed the geodesics. And this will then allow us to calculate geodesics in a much more convenient way than it would be possible by working with a parallel transport directly. So nobody who is working with pseudo-Riemannian metrics will ever calculate geodesics with the help of this parallel transport rule. One would always use the variational principle because it's much simpler. So my claim is the following. I could write this, I could call it even a theorem. Maybe it's a rather big word, but anyway. My claim is the geodesics of the Levi-Civita connection of a pseudo-Riemannian metric metric G are the solution curves of a variational problem. It works in the following way. the Lagrangian is the following. Remember from classical mechanics, the Lagrangian has two slots. In the first slot, I put the coordinates on the base manifolds. In the second slot, I take the derivatives. So the coordinates in the Lagrange formalism, most people, I think, call them Q. But I usually write X for the coordinates on our manifold, so I stick with X. Yeah, so this X corresponds to the Q in most familiar mechanic textbooks. And then I have here the derivatives, the X dots. Yeah, so this is x1, x2, x3, and so on, depending on what's the dimension of my manifold. And this is x1 dot, x2 dot, x3 dot, and so on. And for this variational problem, I consider the following Lagrangian. I have a pseudo-Riemannian metric, G. So I have in local coordinates these things which depend on the x. And I can then do x mu dot, x nu dot. That's a well-defined function if I have a metric. Yeah? The g mu nu's depend on x, and then I take this quadratic form in the velocities. And the action is, as usual, is the integral over L. And now I insert curves. Well, the curve parameter usually is called T in mechanics, but I would like to call it S, because in relativity we very often have a coordinate, which is denoted T. And this would lead to confusion later. So the curve parameter is called S. That's what is usually called T in mechanics. Yeah? And then I have to insert here my curve x of S, x dot of S. So the dot means derivative with respect to S. So that's how you define. And then the variation is delta W equals 0. And the variation has to be done with fixed endpoints. Yeah? So I do the following. I give prescribed endpoints, and then I consider all sort of curves, x of S, which connect two fixed endpoints. And then I calculate for each point, I calculate this here. Yeah, this is a well-defined function now along the curve. So if I insert my trial curve, I get something which depends on S only, and this can be integrated. This gives me the value of the action for this curve. And I do this for a family of neighboring curves. And if the differentiation, the delta, that's something like a derivative with respect to the variational parameter. So it's a derivative transverse to the curves. If this is 0, this means if this is a stationary point of this action, a minimum, a maximum, or a saddle, then I say it's a solution point. It's a solution curve, sorry, a solution curve. And my claim is that if I do this for this Lagrange function, then the solution curves are precisely the geodesics. Yeah? So that's what I want to prove now. And of course, we have to recall some basic facts from classical mechanics. So what you prove in classical mechanics quite generally, that the solution curves of this variational problem for an arbitrary Lagrange function are the so-called Euler-Lagrange, are given by the Euler-Lagrange equations. Yeah? So the solution by classical mechanics. So of course I cannot repeat this here, so I just have to hope that everybody remembers this from classical mechanics. The solution curves to the variational problem are the solutions of the Euler-Lagrange equation. And how do they look? So what is usually called T is now called S here. D by ds, dl by dx mu dot minus dl by dx mu is 0. And I hope everybody remembers this. So I just have to write down these equations for our L. And the hope is, or the claim is, which I want to prove, the claim is that this gives the geodesics. So let's do this for our L. what do I get? I get d by ds. And now I have to take the derivative of this here with respect to x mu dot. Then I get g mu nu x nu dot with a factor 1/2. And then if I differentiate with respect to this term here, I get the same thing because g mu nu is symmetric. So this 1/2 is killed by the fact that I get the factor twice. So that's what I get. Yeah, that's the first term. And the partial derivative is under the derivative. And the partial derivative, there I have to, it's bad that I use the called the index mu, so I have to use a different letter here. So I have to call the summation indices, I don't know, say nu and sigma. Nu sigma x nu dot x sigma dot. Because this is independent of x, the derivative acts only on this here, and the whole thing is 0. You see this? Well, here I have to use the product rule, of course. So first I leave this constant. Then I get x nu double dot. Dot means derivative with respect to s. And this I have to do with a quotient rule. Yes, sorry, with a chain rule. X nu dot, and this gives me a derivative partial sigma g mu nu x sigma dot. Yeah? That's the derivative of this here. The d by ds applied to this here. Let's give this here with the chain rule. I first differentiate with respect to x sigma, and then I differentiate x sigma with respect to s. And the other term is this here, minus d mu g nu sigma x nu dot x sigma dot is 0. Okay, let me see if I can arrange these things. So I want to solve for this here. So I put the other two terms to the other side. They both come with x nu dot and x sigma dot. Because I'm on the other side, this has a plus sign now. So this is d mu g nu sigma minus d sigma g mu nu. Oh, I got a sign mistake. Nu sigma. Where did I make a sign mistake? Just here. Look, there was a minus sign. I forgot this minus sign. So this becomes a minus, and this becomes a plus. Okay? No, what am I doing? No, sorry, this comes from this term. This was nonsense. No, this was correct. What about the sign? Nu sigma. What did I do? These terms have the wrong sign. How can this happen? Nu dot sigma dot. Yeah, hell, what has happened? Well, first of all, I forgot a 1/2, right? Let me see. When I differentiate this term here, that's what I did here, right? I think here I forgot a 1/2. Here it is killed, because I get the term twice, right? But here it is not killed, so here I have a 1/2. Is this much of a help? Let me see. So I have here 1/2. But that was not my main problem, I think. So now this comes with a 1/2. Let me check. So of course I could write this as, well, because here I have x nu dot x sigma dot, which is symmetric. If I interchange the two indices, I could also interchange the two indices here. So I could write this as x nu dot x sigma dot, 1/2 d mu g nu sigma. And then I could write this term twice, once in this form, d sigma g mu nu, and then with sigma and nu interchanged, because it doesn't matter if I interchange the two indices. So that would still be the same thing, right? G mu sigma. But if I'm not very much mistaken, then now I have a sign with, no, I don't, sorry, I don't, I'm stupid. No, everything is fine. Everything is fine. Sorry for this. So what I have to, well, it was a stupid idea to take this to the other side. This had confused me. I should have left it on the other side in the first place. So then I wouldn't have had this problem, because then I get g mu nu, sorry for this. If I leave it on the other side, I get precisely gamma nu. Okay, let me do it slowly. Let's not rush. So let me write this again. G mu nu x nu double dot, and I take it back to the other side again. Sorry, this was a stupid idea to take this to the right-hand side. So I have it on this side, and these two terms come with a plus, and this comes with a minus, right? So I have now, I can write the 1/2 in front of everything. And I have these two with a plus, g d sigma g mu nu, plus d nu g mu sigma. And then I have this with a minus sign. Minus del mu g nu sigma. Okay. And then I want to solve for the x nu double dot. So I would need an inverse of the metric with what indices? The mu is a free index, so I need an upper mu, say g mu lambda. So then I get here g mu lambda g mu nu x nu double dot plus 1/2, or let me write it in this way, x nu dot x nu sigma dot 1/2. Then this here, g mu lambda, and then this bracket, d sigma g mu nu d mu g mu sigma minus d mu, g nu sigma. And now if you look carefully, you see that this is precisely, and the whole thing is 0. I forgot the 0. This is precisely the expression, do we have it still on the board? Which we have found for the Christoffel symbols of the, no, I have erased it already. But that what we just calculated 20 minutes ago or so, these are just gamma mu, gamma lambda, mu is summed away, and the lower indices are sigma and nu, And this, of course, is a Kronecker. This is delta, lambda mu. So I've got the following expression, x lambda double dot. Oh, what is this? I have 3 nus here, that's bad. This should be a mu, sorry. So I multiplied with g mu lambda, yeah? Mu lambda, and then this is a nu, and now everything is fine. So the nu becomes a lambda. And here I have gamma lambda sigma nu and sigma dot x nu dot is 0. And that's excellent, because that's our geodesic equation. And how do we see this? That's the geodesic equation. If you don't see it, I can rewrite it in a little bit more obvious way. The geodesics were defined by the property that the tangent vector field is parallel. Yeah? So I claim that this expression says that the tangent vector field is parallel. So let's write capital X lambda is x lambda dot. So then I have here capital X lambda dot plus gamma lambda sigma nu x sigma x nu is 0. And the dot I can write in the following way. I apply first the the partial derivative to it, and then I differentiate along the curve. Yeah, x mu dot is the same as capital X mu. I could write it in this way. Yeah? Or let me do it step by step. Let me first write it in this way. So instead of putting a dot on it, which means d by ds, I write partial derivative with respect to x mu and x mu dot. This is d by ds, right? You see this? That's d by ds, that's a dot. So, and now hopefully everybody recognizes that this is parallel transport, x sigma x nu equals 0, because it says this is capital X again, right? So this is just capital X mu d mu x lambda plus gamma lambda. I could make this index into a mu. So no, not here. Oops, here. I can make one of the two indices into a lambda, into a mu, lambda sigma nu x mu. And no, the sigma is now a mu. Yeah, this is 0. And now I hope everybody sees that this is parallel transport. Yeah, because this is a partial, this is a covariant derivative. So, oops, let me write the last line also. So this means that, oops, I think I don't. Oh, that's very bad. So this last equation really means that the vector field capital X, which is a tangent field to our curve, yeah, it's little x dot, that this is indeed parallel along the curve. Yeah, I hope everybody sees this. So I can write this in the way x mu covariant derivative, mu x, what's the index? Lambda. Lambda is 0. Yeah, so this means x, which is the same as x dot, is parallel along the curve, which is given by this little x. So that's the way in which the geodesic equation comes out in this coordinate language. This means that little x dot is parallel along the curve. And if you want to determine geodesics, do not calculate the gammas from this expression here, and then try to solve this equation, use a variational problem. It's much, much easier. Start from this Lagrange function, yeah, and look for the extremals of this here. So that's much, much easier. It spares you calculating the gammas with this expression here. Actually, it's the other way around. If you want to determine the gamma, the best idea is to start with this variational problem and then read off the coefficients from this equation. That's the quickest way to determine the gammas. So usually you wouldn't work it out from this expression directly. So you can, of course, you get the same result, but it's not very convenient. So whenever you deal with geodesics, try to work with a variational problem. So now I have 10 more minutes? Yeah. Okay, then I can at least finish this mathematical chapter so that tomorrow at the beginning we can, don't have to erase this. So I don't have to come back to this mathematical stuff. So tomorrow we can then talk about physics again, eventually. So the last thing I want this concludes this here. Yeah, that concludes the proof. So we have learned how to calculate geodesics. We do it with this variational problem. We start with this Lagrange function. That's a convenient way of doing this. And now, at the end of this section, I will tell you a few more formulas for the curvature of the Levi-Civita connection. So the curvature of the Levi-Civita connection satisfies some more identities in addition to the identities any curvature tensor satisfies. Remember, we had a couple of identities, for instance, these famous Bianchi identities and two other ones. The curvature of the Levi-Civita connection satisfies the following. The claim is that, remember, the curvature tensor has 3 slots. Yeah? When you could do the following. You could insert x, y, and z. You could insert this into the metric tensor in one slot. That's a vector field again. Yeah? R eats 3 vector fields and gives you a vector field. And if you fill this into the first slot and an arbitrary vector field u in the second slot, then the claim is that you can interchange these two things and you get a minus sign. So that's the same as minus g r x y u comma z. And what you have to use in order to prove this follows from, it's not quite a short calculation, so you need a few lines. It follows from this expression, from this metricity condition. So if you have an arbitrary connection, curvature tensor of an arbitrary connection, which is unrelated to this metric, then this rule, of course, will not hold. But if it is the curvature tensor of the Levi-Civita connection which satisfies this metricity condition, then it does hold. So in local coordinates, this can be written. Well, what are we doing here? What are we doing here? The R has 3 indices, say mu, nu, sigma, and an upper index, which was here. And if you insert this in the metric, then you pull down this index. And I'm always careful not to write one index over the other, so it's clear that you pull it in this place. So let's pull this in this place. And now the claim is that you can get the same thing with a minus sign if you interchange this slot. This was originally the last one in the R, so it corresponds to the sigma. If you change this with the u, the u was the one which was alone in the second slot. That corresponds to the pulled index. So I have R sigma, mu. Oh, I have 3 nu's. That's very bad. So let's call this lambda. So what do I do? So the interchangement is between lambda and sigma. So it's sigma, mu, lambda. So that's another identity which only the curvature tensor of the Levi-Civita connection satisfies. And the second property is it follows from this one. Namely, this has a consequence that the Ricci tensor is symmetric. So the second property is that R mu nu, which was defined in the following way, that we contract over the first pair of indices. This is the same as R nu mu. So this follows from the preceding identity and first Bianchi identity. So that's the second one, which in general the Ricci tensor is not symmetric. The Ricci tensor of an arbitrary, which derives from an arbitrary connection, is not symmetric. But the one which is associated with the Levi-Civita connection is. So as we always use in the following, the Levi-Civita connections, we will always have a symmetric Ricci tensor. And then you can do a third thing, which in general you cannot do with a connection if you don't have a metric. So if you do have a metric, you can contract another time. Third property is we can define the scalar curvature. That's something which is not defined for an arbitrary connection. It's only defined if you have a metric. Define the scalar curvature, which is, the Ricci tensor has 2 indices down. So without a metric, we couldn't do another contraction, right? There's no way of summing over these 2 indices. But if you have a metric, we could pull up the indices and then we can sum. So this makes sense. And that's what we call the Ricci scalar, or the scalar curvature, or Ricci scalar. That's the same thing. And we will talk about these quantities later. So this could also be written in this way. Yeah? Or because the Ricci tensor is symmetric, can also be written in this way. That's again the same thing. So here we have not only this thing with 4 indices, this general curvature tensor, and the thing with 2 indices, the Ricci tensor, but with the help of the metric, we also have a scalar quantity which characterizes the curvature. Of course, it contains much less information than the curvature tensor with its 4 indices. Okay, so much for the mathematical stuff. And unfortunately, I didn't manage to get far enough so that we could talk about physics already today, but tomorrow we will talk about physics. Then we will see how all these things we have discussed now fall in place in order to establish the formalism of general relativity. So the next chapter will be entitled Foundations of General Relativity. And we will set up the general formalism, discuss the interpretation of basic quantities, and then come to the field equation, which is a new subject. And then we will discuss a few solutions to the field equation, in particular the Schwarzschild solution, which will keep us busy for 2 weeks at least. Okay, see you tomorrow.